Hi everyone. What we're going to do now is work on this problem right here, which is an example of a 2D particle equilibrium problem. This is problem number 1 from the old exam problems. And what we can see that we've got is two cylinders, A and B, that are hanging from three ropes. Rope CD, which is inclined at a 3-4-5 triangle. Rope CE, which is inclined at a 45-degree angle relative to the horizontal. And cable EG, which is inclined at a 30-degree angle from the vertical axes. The two questions that we're asked to do in this particular problem are to draw a free body diagram of all of the necessary components to solve, and part B, to solve for the tensions in cable CD, CE, and EG, as well as find the weight of the cylinder B. The one thing that we are given, in addition to the dimensions and angles and everything, is the fact that cylinder A weighs 50 pounds. So, since cylinder A is the only thing that we know to begin, what we're going to do is we're going to first draw a free body diagram of point E, because that will include cable CE, the weight at A, and cable EG. This is a good strategy because if we know this thing right here, the two things that we won't know are the force in this cable and the force in this cable. However, two unknowns, we're able to write the sum of the forces in the x and the sum of the forces in the y, so we will be able to solve. So my first step in this question here is going to be to draw a free body diagram of point E, and I'm going to do that right now. So now I've drawn a free body diagram of point E. What I've got is the weight A going straight down. I've got cable EG going up and to the right, and I've got cable CE pointing down and to the left. Remember that if we're drawing a free body diagram of point E, we're drawing the cables, and the tension in each cable is always going to pull away from that point. I've included my angles, and I've also included my XY axes. So now we're ready to go and start to write our equations. So the first equation that I'll write is the sum of the forces in the x. I'll set this equation equal to 0, and if we look, I'm going to have both of these forces here. Force EG will have an x component, and cable CE has an x component. So that's it. Those are the only two forces I have. Therefore, what I'm going to have is CE x, which is going to the left. That's going to be negative CE cosine of 45 degrees plus EG times the sine of 30 degrees, because that's across from our 30-degree angle, whereas this CEX is going to be adjacent to our 45-degree angle. So I'll write that out here just so we're all on the same page. This is component CEX, and this is component EGX. Now what you can see here is that right now we've got two unknowns. We don't know CE and we don't know EG, but what we'll do is we'll solve for one in terms of the other. And I did this, and this got me that EG is equal to 2 times CE times 0.707. Essentially all I did was I moved CE cosine to 45 to the other side. Cosine of 45 is 0.707. Sine of 30 is 1/2. So I multiplied that both sides by 2. That gets me EG in terms of CE. This equation is unsolvable, so I need to write another one, which is going to be the sum of the forces in the y equation. I'll set that equation equal to 0, and that is going to get me a couple things. Well, if we look EGX, there's also an EGY, which I'm drawing here in blue, and we also have a CEY as well, which I'm drawing in blue. And we'll have the weight. So what I've got is that CEY is negative CE sine of 45 minus the weight at A, which we know is 50 pounds, plus EG cosine of 30. Now you can see here we've got two unknowns, CE and EG. So I'll take this value from above and plug that in right there. And then I can simplify all of this. So this will get me the equation that 0 is equal to negative 0.707 CE minus 50 plus 1.414 CE. That's what this term is right here, is 1.414 CE. And then I'll multiply that by the cosine of 30, which is 0.866. Now you can see this whole equation is in terms of CE. I'll do one more quick simplification here so you can really see the whole process. So we get 50 equals negative 0.707 CE plus 1.225 CE. So all I did was I moved 50 to the other side. I multiplied these two terms together to get 1.225, and I just kept that the same. Now we just add these two terms together, get everything in terms of CE. So really what this becomes is that we've got 50 equals 0.517 CE. This tells us that CE is 96.57 pounds. Now what we can do is we'll take this value right here and I will plug it in to this equation over here. That will get me the fact that EG is equal to 136.55 pounds. Okay, there we go. We've got everything we need over here. We still need to solve for the cable CD's tension, and we still need to solve for the weight at B. So the next step in this problem is to draw another free body diagram, but this time at point C. So I'm going to get that started right now. So now I've drawn the free body diagram of point C. We've got our point C right in the middle there. I've drawn my XY axes. I've got CE going up and to the right at 45 degrees. And what's interesting here is that at point E, CE was going down and to the left. Over here, CE is going up and to the right. This is because tension only can ever pull away from a point. So keep that in mind. And now I have tension CD, which is inclined in a 3, 4, 5 triangle. And I have the weight at B going down. So once everything's started over here, I can get going with my sum of the forces equations. So I'll write my sum of the forces in the X equation. I'll set that equal to 0. That's going to be equal to negative 4/5 CD plus CE cosine 45. And just to be consistent with what I did last time, we only have two X forces. That's CEX, which you see is the same as what we had before. And we have CDX as well. So we look at this equation. Last time our X equation was unsolvable, but this time, because we have CE already solved for, we can take CE from here, plug that in right here, and actually solve. So fairly quickly, we can find that CD is going to be equal to 85.35 pounds. Box your answer. Then we have one more equation to write, which is the sum of the forces in the Y. We'll set that equation equal to 0. And again, we have two Y components. We're going to have CEY and CDY. So what we write here is we've got CD is 3/5 times CD. So we've got 3/5 CD minus the weight at B going down plus CE sine of 45. Now we plug in what we know here. We plug in what we knew for CE already. We just solve for WB. That's the only thing we don't know. So this equation would simplify to 51.21 minus WB plus 68.28. And at the end of the day, we get our final answer for the last unknown that we needed to figure out. And we solve for WB, which is 119.5 pounds. So now we're done. This is a really good example of a 2D particle equilibrium problem. Effectively, the steps you usually follow is you draw a free body diagram at a point where you have only two unknowns, because you can always write the sum of the forces in the x and the sum of the forces in the y. That allows you to solve by substituting one term into the other equation. Then you kind of just pinball and go to the next spot, draw a free body diagram, and usually at that point it becomes easier because you've already solved for things in the previous step. So there you go. That is this question. Hopefully it helped. All right, everyone, welcome back. We're going to now do problem number 10 from the old exam problems. This is a classic problem that is a 2D rigid body equilibrium problem. You can see it's actually a pretty interesting problem because we've got a distributed load, we've got an inclined force, and we've got a roller inclined on this ramp right here, and a pin at D. We're given all these different dimensions, and pretty much we're told what the distributed load's intensity is, which is 80 pounds per foot. We know that we've got a concentrated load of 390 pounds at this 5, 12, 13 triangle here. We're told what the end conditions are. We're told the angle of the ramp. We're told to neglect the weight and depth of the beam. Thank God for that. And pretty much we have two questions to solve. Question A says, draw the complete free body diagram of our beam A, B, C, D. So we're going to have to draw this L-shaped beam here. That's not too bad. And part B is determine all the reactions at A and D. So let's get started, and I will get us, started more or less with, all right, let's get started. I will draw the free body diagram to begin. So now I've drawn the free body diagram of our system here. I've replaced the pin at D with the reaction forces that a pin can provide, which is an X and a Y reaction force, and I've labeled that dx and dy respectively. I've included the dimension up to the top of this L piece right here, and I've shown at point C that we've got this applied load at 390 with the 5, 12, 13. I've also got these dimensions, and I've got the distributed load right here, and you can see it looks a little bit lighter, and that's because I've drawn it in pencil, because we're going to replace that with the equivalent load in just a second. And last but not least, I've got the NA, which is the normal force applied to this roller, and it's going to be applied normal to the surface that's applying it. Now, one thing that's probably going to confuse a lot of people that would be doing this problem is how do you break this NA up into, the X and Y? I've got my XY axis right over here, and what I've done is I've kind of drawn in pencil here this component in the X and this component in the Y. And what you can see is that I've labeled this angle right here as 30 degrees, which is the same as the incline. Now that's kind of tricky, so what I always recommend is, thinking through it, I use something called extreme case reasoning to figure out why the angle is 30 degrees. So what I've done is I've kind of drawn a very shallow ramp here, and the angle is shown in orange. And pretty much then what I've done is I've drawn like a fake NA, which would be, again, normal to the surface and perpendicular, and then I've gone ahead and drawn an X and Y component as well. And what you can see is that this triangle has two angles, and the angle that looks most similar to this orange angle is this angle up here. That's how you can tell that the angle of the ramp is going to be the same angle of incline relative to the y-axis for your normal force. So when you look at the notes when I upload these later, it might be a little bit easier to see there. But the idea is ultimately that NA is inclined at 30 degrees relative to the vertical axis right here. So pretty much now what we've got to do is probably the first step is I would want to solve for the F equivalent of the rectangular distributed load. And remember that's just going to be equal to the area underneath of the rectangle. So it's the area of the rectangle, which in our case is going to be the base times the height, which is the base is 8 feet across, and the height is 80 pounds per foot. So our feet cancel, and what we get is that F of our rectangle is equal to 640 pounds. So now what I always like to do is I always like to label this in purple because I've got lots of pens. And I've got 640 pounds as our F equivalent of the rectangle. And I want to draw that on our free body diagram now. Now where is that going to act? Remember that the distributed load always acts in the centroid of the shape itself. So because we've got a rectangle, we know that that's in the center. So I can draw that force right here, right in the middle. And that is going to be a distance of 4 feet from the left side. Now what I would probably do is I would probably get rid of the distributed load from our free body diagram, but I don't want to cause all this to get really messy. Just keep in mind that it's in pencil because probably you should have done this first and then put that on the free body diagram. But I just wanted to kind of show you all of the steps to make sure that people didn't get confused and that everything was nice and clear and methodical. So now that I've done this, the things that we can see we have unknown are dx, dy, and na. If you can count, that is 1, 2, and 3 things. So if we have 3 unknowns, we're going to need to write 3 equations. So it's a good strategy here to just jump straight to a moments equation because that's going to allow us to get an equation that's easily solvable in our first step. So where do we want to sum our moments about? That's the question. You always want to sum the moments about a point that has more than one unknown, if possible. Well, where are we going to find more than one unknown in this particular question here? Well, if you look at it right here, point D is going to have a dx and a dy. So this is a prime spot for moments. What we'll do now is we'll say sum of the moments about point D. It's going to equal to 0. And that's going to actually have a couple different things. We're going to have an NAX, which I'll draw here. Oops. I'll draw NAX in red. I'll draw NAY in blue. And pretty much what we're going to show here is that we've got our NAX component is going to move along its line of action relative to point D, and it's going to be located 3 away. So our moments is going to be NAX times 3, and NAX is NA times the sine of 30. So we've got NA sine of 30 times 3, and this would cause everything to rotate clockwise, which we say is negative. So we've got that now, and just so it's very clear, we've got NAX right here, and this is the distance for my moments. So I've got that component. I'm also going to have NAY. NAY is going to cause things to rotate clockwise as well. And because it's a y force, we need an x distance. And the distance from here to point D is going to be 8 plus 4 is 12. So we're going to have minus NAY, which is going to be NA cosine 30 times 12. This is clockwise. So that's NAY times its distance. Last but not least, we're going to have to look at this force right here. If you look, 390 is actually going to have a y component, which is going to go through point D. And it's also going to have an x component, which is going to be distance away of 3. So we have to take that into account. And our equivalent load of the rectangle is also causing a moment. And if this was 4 feet, then what we can see is that this distance over here to point D is going to be 8 feet. So I'll just kind of write this down below this so we don't run out of room. So our equivalent load is going to want to cause things to rotate counterclockwise. So that's going to be 640 pounds times 8 feet. So plus 640 times 8. Counterclockwise is positive. And this 640 is our F equivalent of the rectangle. And the 8 is our distance. So we've got force times distance here. Checks out. Then we're going to have the X component of this force right here, which is 390 times 5 over 13 times 3 feet. So let's make that a little bit more clear here. We're going to have this component here in orange is 390 times 5 over 13. And that's a distance of 3 feet away. So that is this component right here. And that is going to cause everything to rotate counterclockwise about that point right there. And I always like to, if you ever get confused, just put your finger there on your pen, apply a force right there, and you can see what that would do to the system. So this is going to be plus, this is counterclockwise, and from this, what you can see is that the only thing that we don't know is our variable NA. So we can solve for that because we have one equation, one unknown, and this is why it's good to do the moments first. Now what we can do is we can pretty much plug and chug. What we'll find is that we get 1.5 NA plus 10.39 NA is equal to 5,120 plus 450. Now we can isolate all of this, solve for NA, and that will tell us that NA is equal to 468.4 pounds. So now that we've done our sum of the moments and we've solved for NA, now we need to solve for dx and dy. So we're going to write a sum of the forces in the x equation. Set that equal to 0. That's going to be NAX, which as we said before is NA sine of 30. That's going to the right, so that's positive. We ignore NAY, we ignore the equivalent load. We're going to have 390 times 5 over 13, this component right here. That's going to the left, so that's negative, so minus 390 times 5 over 13 minus dx, because I've drawn that to the left. So we know NA from before. This is a number right here, so we just solve for dx, and we get that dx is equal to 84.2 pounds. Yeehaw! Okay, there we go. Now we do some of the forces in the y. Set that equal to 0. That's going to be NAY, which is NA cosine of 30, minus the rectangular load of 640, minus this component right here, so minus 390 times 12 over 13 this time, because we want the y component of that applied force, and plus dy, because I've drawn dy going up, I add it over here. Now, plug in everything we know, and in the end, we will get that dy is equal to 594.4 pounds. Box our answer. And we are good to go, and we've now solved this whole 2D equilibrium problem. Hopefully that explanation was helpful. Let's now look at this internal forces problem. It's problem number 4 from the old exam problems. This is a pretty good one because it incorporates a couple of different and interesting things. We've got a structural beam supported by a pin at A and a rigid link BC. Now, I did mention this earlier on in my lectures, and we'll explain how to treat this in the free body diagram in a minute. We're told that we've got a triangular linear distributed load is shown applied to the beam, and the question asks us to solve for the internal forces and moments that act at point D. And we're told that point D is 0.5 meters to the right of point A, which is a pin. So the first step in any internal forces problem is to identify the point that we want to solve for everything at. And I always like to say, let's draw a dotted line in a different color through that point. The next thing that we have to decide to do is whether we want to look to the left or whether we want to look to the right. Now, remember, you want to be as lazy as possible and find the side that has the least amount of unknowns and the least difficulty in work. So if we look to the left here, we'll have AX and AY and a trapezoidal distributed load. Ouch, that doesn't look fun. If we cut through D and we look to the right, we'll see a triangular distributed load. We don't know this height yet, but not too hard. And we'll have only one force here because it's a rigid link. So this force right here on our free body diagram is really just going to be modeled as a single arrow that way. So if I look to the right, I have two things. If I look to the left, I have 1, 2, 3, 4 things I have to figure out. So it's a no-brainer here. It's not that tricky. I'm going to take this cut and I'm going to look to the right because that is going to be the easier strategy here. So what that means is I have a support in my cut. I am going to have to solve for this support BC before I can go to do the internal forces. So my first step in this problem now is going to be to draw a free body diagram of the whole beam and solve for link BC. So let me draw the free body diagram right now. Now you can see that I've drawn the free body diagram of the whole system. I've got the pin and I've replaced that with its two possible reaction forces, AX and AY. I've got the rigid link BC, which we call two-force member. Its reaction is always going to be inclined along the angle of the rigid link. So we've got BC acting at that point, which is 45 degrees. We've got dimensions showing where every force is acting. And in pencil here, I've drawn the triangular distributed load, which is 500 newtons per meter. So the first step in this particular question is to replace this triangular load with its equivalent distributed load force. So F of the triangle equivalent is going to be equal to 1/2 the base times the height, which is the area of our triangle, which in this particular case is going to be 1/2 times the base, which is 3 meters. It acts over the whole beam, times the height. And our height is 500. So our triangular distributed load is 750 newtons. I always like to then come back and draw this on our beam. Because it's a triangle, it's going to be 1/3 the distance from the tall side. So it's going to act about right here at 750 newtons. And I will say that this is 1 meter from the left, which you can see is pretty much going right there. So we're good. Now that we've got that, I have technically 3 unknowns, AX, AY, and BC. So when you have 3 unknowns, you usually want to take the moments about the pin. That way those things will not be included in my equation. And I can solve for BC right away. So what I'll do now is I'll do sum of the moments about point A. I'll set that equal to 0. That is going to be very effective because I don't need AX or AY now. They go through the pivot point. I'll have 750 times 1/2 meter. That would cause things to rotate clockwise about that point. So that's negative. So we've got negative 750 times 0.5 clockwise. Then we're going to have BC. And BC is going to have 2 components. It's going to have a component in the x direction, BCX, and it's going to have a component in the y direction as well, BCY. Now the component that we care about for our moment is BCY, because BCX, if drawn where it's really acting right up here, goes through point A. So BCY is going to go and cause everything to go counterclockwise. So that's going to be a positive. So we're going to have plus BCY, which is BC times the sine of 45 degrees, times the distance to point A, which is going to be 1.5 plus 0.5 gets us 2. So you can see from this equation we can solve for BC, and that's going to be equal to 265 newtons. Now this wasn't our final answer. We're asked to solve for all the internal loads, but the whole reason we did this was because our cut, when we look to the right, includes a support. We need to know what the support reaction is to be able to solve for the internal loads. So that's why I did the free beta diagram of everything, came down here, summed the moments, and got BC relatively quickly. So now we can draw a free beta diagram of our cut section and now solve for the internal forces. So let me draw a free beta diagram of our cut. So now I'm drawing a free beta diagram of our cut here. We've got the triangular distributed load, which we're going to have to deal with in just a second. And again, I've drawn it in pencil because really we're going to want to replace that with its equivalent load. I've got our force BC, just like before, inclined to 45 degrees. Got the dimensions of our cut section, which is going to be 2 meters total. So you can see that right here. And I've drawn the 3 internal forces, PD, VD, and MD, all in the positive internal loads sign conventions. So really our first step here is going to be to figure out what's the equivalent load of this triangular load right here. Now, the way that I like to do that is with similar triangles. So from before, we know that our triangle had a height of 500 over a base of 3. The triangle in question we're looking at now has a height of h, and it's over a distance of 2. So what this tells us is that 500 over 3 equals h over 2. So this tells us that h is equal to 333.3 repeating pounds per foot. So now what we can do is we can solve for the f of the triangle of our cut. That's going to be 1/2 the base, which is 2, times the height, which is 333.3. And our f triangle of the cut then, we get is equal to, well, not too hard of math right here, 333.3. So that's what this question mark is up here. It's 333.3, and I'll put that over here actually. And now what I'll do is I'll write this in purple, and we'll come over here and put it on our picture. So if we look, the base is 2, so we're going to be 1/3 that distance over from the left side. So I'll just draw it about right here, so it's fairly easy to see. So we get that this is 333.3, and it is located at 2/3 meters from the left edge. Now we're all set up and ready to go. So let's solve for everything. First step, we'll solve for the normal force, PD. So we'll sum the forces in the x direction. So that's equal to 0. That gets us negative PD minus BC times the cosine of 45. So when we plug in the fact that we knew that BC was 265 newtons from before over to here, we'll be able to solve for PD. And what we find is that PD is equal to negative 187.38 newtons. And because it's negative, that just means that our arrow should have been drawn the other way, which would be a negative internal loads convention, which means compression. Now we'll do our sum of the forces in the y direction. We'll set that equal to 0, which is going to be equal to VD going up minus our triangular distributed load, 333.3, plus BC times the sine of 45. When we plug in BC, subtract 333, what we find is that VD is equal to 146 newtons, which is a positive internal loads convention because we get a positive answer. Last but not least, we'll do our sum of the moments about point D. We'll set that equal to 0. That's going to get us negative MD because we've drawn that clockwise on our coordinate axes, minus the effect of this triangular distributed loads force is going to cause things to go clockwise as well. So we have minus 333.3 times 2/3 meters away. That's also clockwise. Then we don't worry about BCX because that would go through point D, but we will have to worry about BCY. That would cause things to go counterclockwise. So we have BCY, which is BC sine of 45 times its distance away, which is 1.5 meters. And this would cause things to go counterclockwise. That's why we say it's positive. Now, if you look right here, everything is all set up for us. We just need to solve for MD because we know everything else. And what we get at the end of this calculation is that MD is equal to negative 58.87 Newton meters. And that is a negative bending moment, so it means that's causing the beam to frown at that particular point. So there you go. For an internal loads problem, you kind of see the strategy we took. We made a cut. We decide whether we want to look left or right. We pick the easiest side. We solve for any support reactions that we need to. Then we draw a free body diagram of our cut, including the distributed load. We find the equivalent distributed load for that particular piece. And then we do the sum of the forces and sum of the moments about that point to solve for all the internal loads. And we make sure that we're including the proper sign for all of them and the proper units. And that's it. That's what you do for an internal loads question. Congratulations! You've now finished all of the lectures and all of the content that's going to be on your first exam, which is coming up very soon. In order to wish you all the best of luck and to ensure your success, I've come to good old Testudo here to make an important donation to make sure that you all do well on your first exam. That special gift I'm going to give Testudo is, of course, my favorite red Expo marker. Oh please, Testudo, accept this gift from me and my ENES 102 students. Let them do extremely well on their exam soon, so that it is much easier for me to grade, and so that they are happy and content in life. Thank you, O Testudo. Good luck on your first exam. Y'all are going to do great.